do is mostly beams that are free space. You launch them onto the trap through a window in the vacuum system.
Right.
And they actually run fibers into the vacuum system and onto the chip. And then on the chip, they have waveguides
Okay.
and launchers. It's basically gratings that bring the beams up to the ions. And we will probably start to collaborate with them because that's something, if you really want to scale up, that's something very nice.
Yes.
And also for other reasons. Your beams will never move relative to the ions. If you launch that closely to the ions.
Yeah, very sturdy. Yes, very sturdy.
Yeah, for us, the beams that are not quite perfectly registered to the ions is always a problem. We always have to change the position a little bit, recalibrate them, realign them to the ions. And if you have waveguides on the chip, you don't need that.
Yeah, right.
In fact, you can move the ions a little bit so they're better on the beam then. It's very tight.
Yes.
Better than a micron precision. Okay, I think you have to go live soon.
Yes, maybe in another. Let's just wait for a minute or so. I see still not many people. Let me also send a message. Yeah. And the protocol for this fabrication and all, these are all available in the literature, publicly available, or these are things which are kept under?
Oh, that depends.
Okay.
So certainly what the companies do, some of it is in the literature, but not, for example, how they fabricate their chips. And for Sandia, I think what's on the surface of the trap is in the literature, but how it exactly looks on the inside is not really publicly known.
Okay.
So it really depends. And for us, everything we do is in the literature.
In the literature, yeah.
Yeah, so our policy is that we are completely open. In fact, NIST is a government institute, and we are supposed to work for the people of the United States. And there are no secret or, classified research activities, at least in our group. We always wanted that to not happen because we want to have grad students and postdocs that are international, and it's not really compatible if you have things that are classified and you want to have international students and postdocs. But we very much appreciate that people from all countries come to us and work with us.
Right.
You have a much higher chance to really find good talent if you can have people from all over the world come to your group.
Yeah. Okay, great. So I think, so we think people have poured in now somewhat more. So maybe we can get started.
Okay.
So Gobi, are we ready?
Yes, sir, we are ready.
Okay.
We can.
So, welcome everyone for the second day and the evening session again. So again, this talk will be given by Professor Dietrich Leibfried from NIST, and he will be talking again on trapped ions. Welcome, Professor Leibfried.
Thank you. I will share my screen now. Actually, okay. I just have to do one more thing, get rid of the Zoom bar that's on my screen here. Okay, and now we're ready to go. So welcome back, everybody. Good evening to everyone in India. And today I will continue pretty much where I left off yesterday, the plan is basically to now take the concepts that were introduced yesterday and put them to work for many ions. So yesterday, everything was about a single ion. And today we will talk about what happens with many ions, how do they behave in ion traps, how can you cool them, and then I'll also talk about an idea of how to scale up ions as carriers of quantum information for quantum information processing. And for that, it's necessary to transport and separate ions from crystals where there are more than one in a certain trapping well to situations where they're in separate trapping wells. So that will pretty much cover it. And if there's enough time, I'll quickly talk about one of the cutting edge experiments that we've done using all these ideas, and then some more. So let's get started. The first thing I want to talk about is what happens if you put several ions in an external potential. And to begin with, I want to leave the shape of the external potential pretty open. So it could be looking like this. And then if you have an ion in a potential and the other ions is fairly far away, something like more than a few 10 microns, there's very little interaction. But these ions are charged. So there's always Coulomb interaction. And when I say very little interaction, what I mean is that this trapping well here and this trapping well here leads to confining terms for the ions that are much larger than their Coulomb interaction. So to first order, the ion just sees the trapping potential and then a very small perturbation, maybe the Coulomb interaction. This situation changes drastically if you have two ions in the same well, because then the well forces and the forces between the ions, the Coulomb force, will balance. And since there is this charge, these ions want to avoid each other, and they typically in a trap that has trapping frequencies on the order of a few megahertz, they will be a few microns apart, and essentially their interaction is of the same order as the external confining forces, and I'll explain a little more what all that means. But to set up the theoretical situation, we're looking at an external potential that can have more or less any shape, and there are n ions in this potential. So the index over the ions here runs from I to n, and this is a three-dimensional potential, so you have three coordinates of the ions in here. And then there's also the Coulomb interaction, and for that, to get the proper distances here, you also have to have pairs of ions. So basically here we are going over two indices to n because it's always pairwise Coulomb interaction. And this is basically the term from the Coulomb repulsion. And if you're in an equilibrium, that's always true. The total force on the ions have to vanish. That means you have to take the derivative of the potential relative to all these positions, and these derivative, the forces, have to vanish. And that will then lead to an equilibrium position. In more detail, we can look at two ions. This is a particularly simple case, and there it becomes really clear how this works, hopefully. Basically, there's the Coulomb term, and we also have decided here that ion 1 is to the left of ion 2. So on a z-axis that runs from left to right, the position of the second ion is always larger than the position of the left ion, sorry. That just means they can't jump over each other because the Coulomb potential is so strong that they don't really want to change places. And so the Coulomb terms are just equal and opposite for each of them. And this has to then balance with the external potential. And as soon as the force from the external potential and the Coulomb force is the same, you have reached equilibrium. And of course, this is true for both of these ions. So that an equilibrium can exist in the first place, you have to have these two conditions. The external potential has to have a negative slope on the left-hand side and a positive slope on the right-hand side. So you can balance the Coulomb repulsion. And then also the ions, no matter what crazy shape the potential has, the ions will have to balance in such a way that they see the same force, equal and opposite from left and right. So it just balances their Coulomb force. That's the basic requirements, no matter what this potential looks like. We can now further specify and say we also look at a particular symmetric well, and this is useful later on. You'll see why. And if it's symmetric, it basically has to have even powers in the position. So here a c to the second power term and a c to the fourth power term. The reason why these two terms are particularly interesting is that I can basically form situations where I go from a completely harmonic potential. So in this case, this spring constant K would be non-zero, and K4, the quartic coefficient, would be 0, and I have a harmonic potential. So that's the ideal situation we were talking about yesterday for a single ion. We can also go to the boundary case here where the fourth order is non-zero and the second order is 0. So this looks like this very flat potential here. And then finally, we can actually turn the second order term around, so it becomes negative. And then we get the situation where we have a double well. So you can already imagine maybe that if you have two ions in such a potential and it changes from here to here, that the two ions will end up in their separate wells. So this will be interesting for separation. The other point to make here is that you have a general equilibrium condition for any of these cases. So no matter what K2 and K4 are, that looks like this. So it's just a single condition. And the reason for that is that the left ion and the right ions are mirror images of each other. And so when you look at their equilibrium conditions, these conditions are the same up to a sign. And we can just talk about one of them. And that's this condition here. This is not easy to solve in general. You can see that the equilibrium distance shows up in different powers and even 1 over the second power for the Coulomb interaction. So it's not easy to solve unless one of the coefficients is 0. In that case, you get this maybe somewhat familiar equilibrium distance for ions in a harmonic well. You see that often in the literature, just to get an idea of how far ions are apart in a harmonic well. And for the fourth order, you also get an equilibrium distance, which looks a little different. This is to the power of 1/5. And basically what it expresses is that the ions have to move further apart to come to the walls here and get a force from the outside that's equivalent to their repulsion. So they will move apart here already. And then when you go to the double well, they'll move apart even more. And at some point, they will be so far apart that their interaction doesn't matter anymore. So this is the case for two like ions. The next interesting thing is if you can find the equilibrium position, and you can do this more generally than I just discussed in these simple examples, what can happen next? And basically the next order is something that you might be familiar from in a different context. You can have small oscillations. And this is a famous problem in classical mechanics. Basically what you need to do is you have to find all the curvatures of the ions. So you look at the second derivative around their equilibrium position. The first derivative, we already know the sum of all of them goes to 0 because we're in equilibrium. There can't be any force. So the second derivative is the only remaining interesting part to the lowest order that you could be interested in. And this is basically how this curvature tensor looks like. And what you can't forget is that this contains the external potential and the Coulomb potential. And these indices here, you have two now because you have ions, 1 to n, and you also have spatial directions. So that would be 3 spatial directions in the most general case. And you can think of these as the generalized spring constants, but really don't forget that they also contain the Coulomb interaction. So it really depends on what exactly, how many ions are in a trap and so on, what they look like. This is not something that's given from the outside. And basically this leads to 3n coupled equations of motion. Looks pretty nasty, but as you'll see, in the case of these small oscillations, we can actually make several simplifications and arrive at a new picture that's much more useful. So basically, again, this is the same equation of motion. You have the second derivative with respect to time here, and then you have the same amplitudes, small amplitudes around the equilibrium positions here. So this here and here is the same. If you have a single mass, you can just take the mass and put it under here, and then you basically have something that just has the coordinates. But if the masses of different ions are different, you can't have this nice situation as easily. But there's a simple trick that you can play. You can mass weigh your coordinates. So what you do is you just multiply your small oscillations by the square root of the mass of the ion that you're talking about. So index I here. And if you do that, you basically get a new coordinate, x tilde, delta x tilde here. And on this side, since you can just plug that in and then divide both sides by mi, then you get this coordinate here, and your mass tensor, your curvature tensor is changed because you now have the square root of mi and mk below it. So basically now by mass weighting these coordinates, I have created a situation where I just have the second derivative with respect to time over here, and then I have a symmetric matrix here and just the small oscillation position coordinate. And this is a nice situation because this is a symmetric tensor, and typically if the equilibrium is stable, which we need anyways because otherwise our ions will fly away, then you can actually solve this and you get free n eigenvectors and eigenvalues. And these eigenvalues are called the normal mode frequencies, and the eigenvectors are the normal mode vectors. Formally, they look like this. Instead of having this horrendously coupled case, you find these particular coordinates q that actually diagonalize the whole problem. So instead of having all these coupled oscillations, you now have normal modes, and each of them can be thought of as basically being independent. And at this point, you can then also go to a quantum mechanical picture. You just take these so far classical amplitudes and put quantum mechanical operators in for the normal modes. So really what we want to talk about with several ions in a trap are their normal modes. To make this a little more intuitive, I want to illustrate it. So the first example I have here is I have two ions, but the well can be to the second and the fourth power. And so I just want to look at what happens here. Because we have the same mass, we can just divide by that mass for the curvature matrix. And then we have diagonal terms that have the external potential. So this is just what I get from the external potential if I take the second derivative with respect to z. And there's the equilibrium position in here. I have to do this at the equilibrium point. And then I have the Coulomb force. For the off-diagonal terms, there's just the Coulomb force. So this is basically what it looks like for any situation, no matter what k and k4 are. And it turns out that the eigenvectors of such a matrix are always the same, no matter what k and k4 are. They're basically what we call the center of mass motion. Both ions have the same amplitude, so the whole crystal moves as one unit and just the center of mass moves. That's where the name comes from. And the other one is the stretch motion, where the two ions move out of phase. They basically increase their distance or come closer together. And the frequency, depending on k and k4, for the center of mass looks like this. And then for the stretch mode, the frequency is always higher than the center of mass because you have to push against the Coulomb force and pull against it, against this equilibrium to get this. So you get this extra term from the Coulomb interaction in the stretch mode. So basically, the mode splitting is governed by the Coulomb interaction at the equilibrium distance. And you can write this down in this simple case, and it's all analytical and pretty easy to understand. The next example I want to give you is that things change quite a bit when the masses are different. So let's take an example where I have a big mass, capital M, and a smaller mass, lowercase m, and the ratio of the two masses is larger than 1 m over m. In this case, I'm just talking about the harmonic potential to make it not too complicated. In this case now, we have a mass-weighted curvature matrix. So you can see, depending on how often mass 1 shows up in a certain term, once or twice, you get these factors of square root of mu or mu in here. And then the whole is divided by 1 over m. So this is the mass-weighted curvature matrix. And the bare spring constants are also mass-weighted, as you can see here, depending on which one we're talking about. The eigensystem looks pretty complicated, maybe. There are a lot of terms that go with mu here. And of course, you have two different eigenvectors of the motion here. But once you look at this for a while, it's not quite so bad. And for example, if you make mu equals to 1, so you have the same mass, you will rederive the square root of 2 for the center of mass, 1 over square root of 2 for both of them, and minus, because of this minus and plus sign here, minus 1 over square root of 2 and 1 over square root of 2 for the stretch mode. And similarly for these frequencies. The other interesting case is if this ratio here goes to a very large value. So one ion's really heavy and the other one is really light. In this case, you get two modes of motion. One of them is just the light ion oscillating. So that's the higher frequency because this light ion can oscillate much faster in the same external potential plus its heavy companion, which is basically just a part of the external potential. And then there's the other mode, and you can see that both ions participate. However, if this mu goes to infinity, the mode frequency goes to 0 of this mode here. And what this just means is that you have a humongously heavy second ion, and that second ion is hardly moving no matter how hard you push it. And the frequency goes to 0 because it's just so inert. And then the other one is basically a single ion, a light ion in the potential where you have the external potential and the Coulomb interaction from this heavy friend. And so the frequency is a little bit higher than what it would be just in the external potential without the heavy ion. So this is fairly intuitive what happens here, despite the fact this maybe looks pretty nasty. So after talking about what kind of normal modes you get and telling you that you can look at the normal modes completely decoupled, so you basically have the same problem that you had before for a single ion, but now when you talk about the motion, you're not talking about single ions, they're all coupled together, you're talking about single normal modes. And so these normal modes basically have a life of their own, but they're also great because they couple all the ions. And that is really what we use in our experiments to do quantum logic and things like that, that you will learn in the other lectures. So if we add the light field now, it basically looks the same as what we had yesterday. However, we have to also sum over all ions that actually interact with the light. So the situation I'm imagining here is that you could have, again, different species of ions, and maybe not all of them interact with the light. So when you sum over the light interaction, you have to think about which of the ions actually interact with this light. And so I have to think about it and which of them don't. And the ones that do are basically this set of J here. And I have to sum over all of them. Another difference is that they sit at different positions. So the light field will have a different phase on these different positions. The light wavelength is shorter than the typical equilibrium distances. So this phase really changes. And of course, each of them can have their small excursions of the ions. But again, we can now, after we've just looked at this interaction here, we can take the small excursions of the single ions and rewrite them in the normal mode coordinates. So basically, I'm taking this exponent here, and I'm just plugging in the normal mode coordinates. And in that case, you basically get a sum, a product of exponents, and each of them contains the independent normal modes. And you have something like the Lambdicki parameter again here, but it's a bit different. I'll talk about that in a second. And then you have position coordinates for the normal modes, which are abstract position coordinates. They don't correspond to any particular ion. It's basically an abstract quantity. The interesting thing about the Lambdicki factors is that they can be very different from the single ion case. And that is because the mode participation, so how big is the amplitude of a certain ion in this normal mode, enters in here. I have an example that illustrates this a little bit here. Suppose you have a string with 3 ions, and the middle ion could be a different species, and I'm talking with my laser to this blue species here. In that case, in the stretch mode, the blue species has no participation. So no matter what I do with my laser, I will not be able to affect the stretch mode of this motion here, because this Lambdicki parameter here is strictly 0. The participation of the ion is 0 in this mode. And so if I would, for example, try to cool the stretch mode of the whole crystal on this blue ion, I couldn't do that, because the participation that I need for cooling would be 0 in this particular case. So you can basically write down how much participation do I have in a certain mode E for cooling by just summing the square modulus of these Lambdicki parameters for this normal mode. And depending on what that is, you can cool or not cool not so well, or you cannot cool at all in this particular case. So that's how the cooling works. I think this is a good time for the first round of questions.
So I don't see any questions.
Okay.
Yeah.
Then
sure,
I will just continue.
Yes, please.
So to illustrate this a little more, I want to tell you about some simple experiments on ground state cooling of ion strings of more than 1 ion. The first experiment on cooling 2 ions was done in 1998. This was basically an RF trap that was a little bit elliptical, and 2 beryllium ions were trapped in the trap. Here's an image from the CCD camera of these 2 beryllium ions. And these are false colors. So white means you get a lot of photons, red means a little bit less, and then blue and black means almost no photons. So this is mostly stray light. And the 2 ions are sitting here. They're about 3 microns apart. And this trap has, of course, 3 normal modes. And 2 of them were actually cooled. You can see that here. Those are the 2 axial modes. 2 of them were cooled to the ground state. All of them were Doppler cooled. So for the 2 axial modes, we can use the thermometry that I was talking about yesterday. But remember, this is for normal modes now. You're not looking at single ions, you're looking at the normal modes. And basically what you can see here is that after Doppler cooling, that's the lower row, the blue sidebands and the red sidebands are both non-zero. And then after ground state cooling, after resolved sideband cooling, the stretch mode red sideband and the center of mass mode red sideband are almost vanished. So you're in a very low N bar. The thermal state of these ions is very close to the ground state. The way this cooling was done was that you intersperse pulses on the center of mass motion and on the stretch motion. The idea is that whenever you do these pulses and the repumping, you get heating from the recoil, and that determines your Doppler limit. And it's not a good idea to have all the recoil into the unaddressed modes at one time. So you intersperse, you address one mode, then the other, then one mode, and then the other. And in this way, you can reach a lower cooling limit. And so this technique that was used for 2 ions here was essentially used in the same way. You had just more modes to address, more frequencies and sidebands to ground state cool up to 6 ions of the same species. And today, for example, at the University of Maryland, people can cool up to 15 of closely spaced radial modes of ions. There are also experiments with a lot of ions at the University of Innsbruck that I think Christian Roos will talk about in one of the lectures later on. They only cool a few of the normal modes to the ground state, and then the rest of them are at the Doppler limit. But in any case, you can basically choose which normal mode you want to cool, and then you can cool them close to the ground state, even for these larger crystals. For mixed species, there was also a first experiment in 2003 with two masses that are actually quite different. So it was a beryllium-9 ion and a magnesium-24. So the ratio was larger than 2, the mass ratio, almost 3. And for this case, you can see what that does to the normal modes. You basically get this higher frequency mode that I was talking about, where mostly the light ion, the beryllium, is moving. And you get the lower frequency mode where the beryllium and the magnesium ion are moving. The magnesium ion is moving more. And the frequencies are quite different from each other. There's almost a factor of 2 between them here. And so it's not so easy to actually cool both of these ions on just one mode, because no matter which ion you choose for your cooling, the participation of one of them is rather small, 1/√7, and the other one is relatively large. Nevertheless, the cooling succeeded, and depending on whether the cooling was done on beryllium, where we got the better results, we got an N bar of 0.03 on this minus mode here, and then 0.04 on the plus mode. And you can see the results here. This is after Doppler cooling. So there's a little bit of symmetry in the sidebands, which means there's a little bit of population in the n=0 state where you can't drive that sideband. And then after resolved sideband cooling, these sidebands are essentially gone. So we are very close to the ground state, a very small N-bar thermal state. These techniques have been used to great effect in quantum logic ion clocks. And in fact, one of the quantum logic ion clocks we run here at NIST, the aluminum magnesium clock. So instead of beryllium, you have an aluminum ion, which is a much better mass match to magnesium. This clock is actually one of the best clocks in the world. We were also able to expand these cooling techniques to larger crystals, for example, a 4-ion crystal, beryllium, magnesium, magnesium, beryllium. And I already said quantum logic clocks use this technique. I also talked about EIT cooling yesterday, and one thing that was mentioned in passing is that EIT cooling can have a larger bandwidth. And we actually demonstrated this on a beryllium, magnesium, magnesium, beryllium chain, so 4 ions. The situation for EIT cooling is a little more complicated than what I was talking about yesterday. This is magnesium-24, and it has an S1/2 ground state with 2 substates, and a P1/2 excited state that also has 2 substates, plus and minus 1/2 for the C quantum number. And so basically, by using a magnetic field, you can split the S and the P levels in energy. That's what an external static magnetic field does. And you can use a tripod like this. So you would have the ideal EIT situation. However, there is this 4th level here, and there will be transitions off resonantly on this 4th level. So it's not quite ideal, and that forced us to use a bandwidth for the cooling that only worked for 3 of the 2 modes, of the 4 modes, axial modes simultaneously. So if you look at how well can you cool these modes, those are in different colors here, blue, red, green, and black. How well can you cool them versus changing the power in one of the beams, which changes the AC stark shift here. You can see all of them go to fairly low N-bar, but then this red mode goes to its lowest N-bar much earlier than the 3 other modes. So what we ended up doing is to first cool the 3 other modes, and then finally cool this red mode with a different laser beam that had a different AC stark shift. And in this way, we were able to get all 4 of them to a fairly low N-bar. So using this EIT cooling, we were able to go to about an n bar of 0.2 in the worst case. You can maybe see this here in logarithmic scale. And we used a very small laser power, 35 microwatts, for doing this, total power in the EIT beams. And this is possible because your detuning from the excited state, this delta here, is relatively small, just 60 megahertz. The same experiment done with resolved sidebands and much further detuned Raman beams at 9 gigahertz, you need much higher laser power, about 1 milliwatt, and also the cooling time is longer. So basically, there's a trade-off between having relatively short cooling times and the potential to reach very low n-bar. So this is maybe not the lowest n-bar you can reach here. This is just for this example. You can go to larger detunings and get even lower n-bars. With EIT, you're not getting quite that low, but it's much faster and it needs less power. So this is maybe also the more precise answer to one of the questions that arose yesterday. Basically, EIT is really nice as another step between Doppler cooling and then maybe cooling the mode you really care about because you want to do a quantum operation on it with resolved sidebands. One more stage of cooling. All right, so if there are questions, I can take them here again.
Yeah, I still don't see any questions.
Okay, then I will continue.
Yes.
So the fairly long final chapter I want to talk about is the ion transport and separation. Basically, what we are thinking about here at NIST and many other people are thinking about in the meantime. For example, the company Honeywell has picked up this idea and is trying to build a commercial quantum information processing system based on these ideas, is what sometimes called the quantum CCD architecture. The basic plan is to, instead of putting all the ions in a single trap and getting a lot of normal modes, 3n of them for n ions, you can build a trap array. So you have a lot of electrodes here. This is what we call a surface electrode trap, which is particularly suitable if you want to microfabricate traps and make them really small and precise. You can do much better with microfabrication than what you can do by building your traps by hand out of discrete parts. And the basic idea is that you can apply different potentials to all of these electrodes here. And in this way, you can, for example, confine these free ions here by having RF on this and this electrode. So that gives you the ponderomotive confinement of the ions in the radial directions, in this direction and out of the plane. And then you can use these control electrodes to, for example, have one that's more positive than these three here and one that's more positive here, and that will confine these three. You can also change the pattern here, and that will allow you to transport these ions around. I'll talk about how that works a little more in detail soon. But basically, what we would like to do is move these ions and maybe go to this junction here where we can sort them in such a way that, say, the ions we want to do a 2-qubit gate on go to this side, and this other ion is just stored away here for a while until we have dealt with these two ions. Since we're moving the ions around, they might actually heat up a little bit, and there's also something called anomalous heating in ion traps. So basically, there are noise electric fields in each practical ion trap, and they can heat the motion of the ions from the ground state and basically spoil the motional degrees of freedom as a nice quantum degree of freedom. But we can now use these tricks where we can cool two ions of one species with another species. And that means we can use a cooling laser that does not talk to the 2-qubit ions here. So we can now turn on our cooling laser, and by sympathetic cooling, we can cool all three of these ions. You have to be careful that the participation in all of the normal modes is non-zero for this kind of crystal, so you can actually cool all of the modes here that you care about, and in particular the one you maybe want to do a 2-qubit gate on. If that succeeds, you can now do a 2-qubit gate, for example, on these 2 ions. You'll learn more about this, I think, in the next few lectures on trapped ion, quantum information processing, and other nice things you can do with trapped ions. So now maybe I've entangled these 2 ions. I've done a 2-qubit gate, which is one of in the set of universal gates that you need to do quantum information processing. There's also another gate, and this is a single qubit rotation. If I want to do this here, I basically have to remove one of the ions, or that's one way to do it. And then I can use a different laser beam that does a carrier transition. And that can be a single qubit rotation. So basically the single qubit rotations are done by carrier transitions. You only affect the internal state, not the motional state, while the 2-qubit gates are done by using sidebands, typically pairs of sidebands, to do a so-called Murmer-Sørensen gate. And if you've done all of that, you can, for example, also read out the ions. So this is the state-dependent fluorescence we were talking about yesterday. You can shine a resonant beam on these 2 ions. And in the particular example I had here, one of the ions was bright and created a lot of fluorescence that I can see on my photomultiplier or CCD camera, and the other one remained dark. And once I'm done with that, I can bring in new ions, or I can move these ions around. The basic idea is that if you have all these primitive operations working for you, you can think about scaling such a system up and make a universal quantum machine out of it. So there are a lot of moving parts here, and I can't talk about all of them, but I'll talk about a few of them. And in particular, I'll talk about how we can approach this transporting around, which is really easy in PowerPoint. But in reality, if you want to do it with single trapped atoms, you have to think about it a little more precisely. So the basic situation I would like to discuss here is what happens when you transport ions around. So far, we were talking about this part of the Hamiltonian, not the red part. So the equilibrium position was always in the same place for a single ion here. It was, you can make it your origin, for example, and so the Hamiltonian would look like this. But you can also do a transport. And what does a transport mean? It means that you want to move the minimum position of the potential around. And you can model this by having a term here, x0 of t, that changes over time and moves the minimum of the potential when it changes. And then, of course, you have to square this to get the potential energy. We call this x0 of t a transport function. And it basically moves the harmonic well. It doesn't move the ion right away, but it moves the harmonic well and its minimum. And you can imagine if you have a harmonic potential that's moved around, the ion will have to follow that to some extent, but it may also get excited and move around. And that's basically what we want to model. How does the ion respond to this transport function? So as always, we want to solve for the wave function of this ion as this transport function takes action. And the first step we can do is relatively intuitive. We can go to a frame of motion that moves along with the minimum. So basically what we need to do here is we have to do a displacement in the position of the ion. This is called a coherent displacement. And we displace it just so much that the new wave function is displaced by how much x0 has moved at that point. So it's just x0 of t and then multiplied by the appropriate constants of this ion. So you get the right displacement in position space. So now this wave function lives in a frame of reference that moves along with the position minimum. We can just plug this ansatz into the Schrödinger equation. And what you see is two things. The first is you get the static oscillator Hamiltonian back. So H0 is just what we have up here, but X0 of t is identical 0, so nothing happens. That's H0. So basically you have an oscillator at rest for this term here. And then there's this term that goes as the speed of the transport function. So this is not the ion, this is the transport function. How fast does the well move? Times the momentum of the ion. And there's something you can already learn from this. Suppose this speed here is very small. So small that the product of this and that is much smaller than the kinetic energy up here. You have p squared over 2m here. And here I have basically the velocity times p. So if x naught is much smaller than p, then this term doesn't really play a role. And your ion pretty much stays in the ground state, despite the fact you're slowly moving it. This is what we call the adiabatic solution. If the speed of the well becomes comparable to the momentum of the ion over m, then you're not adiabatic anymore. You're actually doing something. And that is expressed by this term. So basically what we have to do is look more closely at this term. What does this term actually have? What effect does it have? To do that, we can get rid of the static harmonic oscillator by transforming into the frame, rotating with the static harmonic oscillator. So basically, we are just taking the evolution due to the fact that you're in a harmonic oscillator out of the problem by doing this transformation here. So this is the second transformation. We've done the displacement with the transport function, and now we take out this static harmonic oscillator energy. Once we do that, we have to do a little algebra, but we derive a very simple equation of motion in this frame. In this frame, you actually have a Hamiltonian describing another displacement on this wave function. And the coefficients of this displacement, so how much displacement do I actually have, are given by the transport function, and in particular by the Fourier component of this transport function, time derivative times the trap frequency. So it's basically a Fourier transform of the velocity of the transport times this constant here to make it a displacement. And so basically, because this is a coherent displacement, if you, for example, think about this state having been the ground state in the beginning, it would describe a time-dependent coherent state. So what happens when you do transport is your ion goes from, say, a ground state to a coherent state, or if you start in a general state that's not the ground state, for example, it could be a thermal density matrix, you get a coherently displaced thermal density matrix. There's also a phase here that would be very interesting if it's state dependent, then you could make a gate out of it. That's basically how gates work. But in this case, it's the external potential that's driving the ion. And all the external potential does is it couples to this charge of the ion, not any of the internal states. So all internal states are affected in the same way, and you can't get a gate from that. We can actually forget about this phase because it's just a multiplication factor to the motional wave function, and it doesn't have any effect on the dynamics. So once we do that, we can look at what has happened in total as a function of the original wave function here in the original frame. What we've done to it is we've done this displacement due to the transport function. We have gone to a rotating wave that takes the static Hamiltonian out. And then finally, we have moved the well along with its transport function. And this is the effect of all three of these operations together. And what we will get here is a coherently displaced state according to the transport function. We can look at this in a little more detail again. We can think about limiting cases. As I already said, you get something like the Fourier transform of the velocity of the ion. And basically, if you want to get an ion at rest in the final place, so the displacement here describes I go from the initial place to the place at times t, and this is the evolution of a harmonic oscillator that would not be moved at all. So you're just doing your oscillations in a static potential. And I want this part here, this describes what happens to the motion of the ion other than just doing its usual thing and being displaced. This needs to be 0 if you want to end in the same state in a different place with your ion. So basically what you're asking for is that this d of t, the displacement here, becomes 0. And that means this integral here has to vanish. And it's a Fourier transform of the transport velocity at the trap frequency. You can immediately see, without doing much math here, that you can go to 2 regimes. One is you can make sure that all Fourier components in this transport function here are too small to actually have a component at the trap frequency. So in that case, these velocities are small and you're talking about adiabatic transport. And basically this integral will tell you how adiabatic you are, how small does this number get. You can also go to a different regime where you have actually Fourier components that can be substantial for frequencies that are larger than the trap frequency and smaller or commensurate. But you just make sure that this integral vanishes at the end of the transport. So if I set t here equals to capital T, at the end of the transport, this integral has to vanish. And in between, when t is not equal to capital T, I'm okay if it's non-zero. That just means the ion gets excited during the transport, but at the end of the transport, when t goes to capital T and the integral vanishes, I'm still back in the state that I started in. This is what we call diabatic transport. So during the transport, the ion can be excited, but then at the end of the transport, it goes back to its original state. This really works in practice, so it's not just theory. And this can be done, for example, in an idealized case. It's relatively easy to see what happens. This is an unphysical transport function, so we can't exactly do this in the lab, but we can approximate it. The idea here is to make this integral simple. Let's try to transport the ion at a constant speed. So if t is smaller than 0, the ion is sitting in some place, while t is between 0 and the final tn, it's moving at a constant velocity, which means between here and here, you have to accelerate it with an infinite acceleration. So that's the unphysical part. And then after t, you are at 0 velocity again. In this case, you just have to do this integral with v0 in here. It's a constant. And so this is just oscillating at the trap frequency, this integrand. And in this case, it's fairly easy to see that if I make t the right amount of time, then this displacement will vanish. And in particular, these are the times where the integral goes to 0. So basically, you could have a very large d of t because it will oscillate during the transport, but at the end, you go exactly to 0. And you can approximate this in the lab, and there have been experiments that implement this idea. You can read about it in these references here. And basically, I have a little movie here. I hope I can make it work. It seems like... Okay, here we go. So this is the kind of trap we were using for this experiment. It had several electrodes, and we basically wanted to transport from here to here and use this idea. So looking at the ion more from the side here and also showing you what the transport function looks like, you can see that, I'll just stop the movie for a second here, that the well is moving and the ion is oscillating. You can maybe see it in this curve. The dashed line is the transport function. And the red solid line is how the ion reacts to it. And what you can see is that the transport starts. It has this kink here, which is unphysical. The transport starts and the ion doesn't start moving right away. It basically has to ride up a little bit on the side of the wall before it actually starts moving, and then it overtakes the transport function. Then it lags behind again, it overtakes, and it just keeps going like that. And then at the very end, you're decelerating again in a fashion that is actually an unphysical kink here, but the ion reacts to it in such a way that it decelerates and finally comes to a rest. And so just to keep running here, this is what this would look like. The ion's oscillating during all of the transport, but then when you stop, it just stops as well. And this worked fairly well in the lab. We were able to transport the ion not quite at the ground state, but very close to the ground state by doing that. And this was possible in very short times. So basically we were able to transport from here to here. This is a distance of about 300 microns. And we were able to do this in a time of about 80 microseconds. And that, sorry, not 80 microseconds, in 8 oscillations of the ion. I think it's more like 20 microseconds. And there was a similar experiment at the University of Mainz. So this works and it's fairly robust, it turns out. Of course, if you have more than one ion, this simple scheme breaks down because we're basically making sure that the transport time is an integer multiple of the oscillation periods. If you have several normal modes, you would have to have integers of all these oscillation periods at the same time. And so you can't do it quite that simply, but you can do more complicated math and can also get transport time and transport pattern that works for more than a single ion. Okay. All right, so the next thing I want to talk about is ion separation and recombination. We already laid the groundwork for that by talking about this particular external potential that has a quadratic and a quartic term. And again,
would you like to take some questions now? Can we take
course.
a couple? Okay,
yes,
so we have a couple of questions in the chat box. So the first one is, how do you integrate the light fields on the chip trap? And could you comment on how to minimize the effect of patch potentials?
Okay, let's start with the first question and then you have to ask the second again.
Sure.
So far, we are not really integrating the light fields on the chip. We are using beams that go through vacuum ports in free space, and they are above the chip by about 30 to 40 microns. So it's a fairly short distance, and they're just in free space. In the long run, that will not work for integrating. You will have to have your light fields on the chip. And other groups, in particularly at Lincoln Labs in Massachusetts, and also at the ETH Zurich, at Sandia National Labs, and I think also Honeywell has started an effort to integrate waveguides for the light on the chip. So basically, in that case, you have waveguides that confine the light on the chip and grating couplers. So this is a special type of coupler that can negotiate between this waveguide and free space. It takes a waveguide mode and makes a free space beam, and that free space beam can then hit the ion. And so that would be the way to integrate light fields. Another approach that we're looking at is to actually use microwave and radio frequency fields to do the quantum logic gates. In this case, you would only need the resonant beams for cooling and for state preparation to be in these waveguides. So basically, this is a really tough problem to do when you want to scale, but there are ideas how it can be done, and several different groups and even Honeywell, a company, are working on doing this. So can you repeat the second question, please?
Right. there are two which are related, so I'll tell them together. The first one is, could you comment on how to minimize the effects of patch potentials? And the other question is, for these traps, are there issues of Casimir polder-like effects or surface heating?
So if I understand correctly, this is about heating effects, right?
Right. Yeah, the first one is how to minimize effects of patch potentials.
Okay, great. I can answer that question, hopefully.
Yes.
So what we would like to do, of course, as always, when you miniaturize, is to make everything as small as possible, which means that the ions will be closer and closer to the surface. And as the question implies, there are detrimental effects. We call it anomalous heating. So there's noise from the surfaces that heats up the ions. There are two known ways to minimize them at this point in time. One is you can treat surfaces. In particular, this has been done with gold and also some other metals. You can do ion-ion bombardment, argon-ion bombardment, or other bombardments and clean the surface of contaminants, and that can reduce the heating rates, the anomalous heating. You can also go to cold temperatures. And I think in particular, this last thing, to go to cold temperatures, is a very good idea also for other reasons. When you go to cold temperatures, in particular below 10 Kelvin, you freeze out all the background gas in your trap. And that means you don't have background gas collisions anymore. For small numbers of ions, let's say below 20, background gas collisions are so infrequent that you don't have to worry about them very much. But if you build a big machine that has thousands of ions, you would basically get background gas collisions all the time. And the bad thing about them is that they can kick up your ion crystal and even change the order in the crystal. So at some point you would not know which qubit is which anymore because it could have changed places. So I think the second technique to use cold temperatures is a really nice approach. And in addition, there will be hopefully material science that will help to further reduce the effect of heating. The final ingredient is we would like also for speed reasons to go to higher and higher trap frequencies, so the motional frequencies. And these anomalous heating effects are all scaling with 1 over the frequency squared or to the third power, or it's different exponents, but it's always 1 over the frequency to the power of something. So if you go to higher trap frequencies, you can also reduce the effect of this anomalous heating.
Okay, so I think so the other related question was about this Casimir polder-like effects, if there are some effects like that in these traps.
I think at this point, we don't see this kind of effect. I mean, it depends on what Casimir polder effect you're talking about in particular. But if you're just talking about the fact that the vacuum of the modes, the electromagnetic modes, is modified by the presence of the traps, these effects are extremely small, and it's very hard to see them even for neutral atoms. With the trapped ions, the forces from the trap are so much larger than any of these effects that I don't think anyone has seen them so far. I have never done an estimate how small you have to make the trap to actually see them prominently. That would be a really cool experiment, I think, if you can see that. But as far as I know, they've only been seen in neutral atom experiments so far, because otherwise the Coulomb force and the force from just small patch potentials and the anomalous heating probably would totally swamp the Casimir polder effect.
Right. Okay. So there's another one, maybe this can be short. Could you comment on the fraction of time for the ion transport versus the gate execution time?
Yes, so for adiabatic transport, this time is much larger because gates can basically be executed on the order of a trap frequency or even faster. There was an experiment in Oxford, I think 2 years ago now, where they did a 2-qubit gate at fairly high fidelity, higher than 90% if I remember correctly, essentially in one period of the motion of the degree of freedom that they used for it. I think it was the stretch mode. So this is the timescale for gates that you can at least aspire to at some point if things are really perfect. And the transport has to be diabatic. So in the regime where you're moving the ions during the transport fairly rapidly, and then you have to bring them to rest. So you have to have this diabatic transport, and probably you also have to have it for mixed species. This is an active field of research, and there are no good answers at this point how you will do this. But I'm fairly hopeful that it can be done. It's just a matter of figuring out how to do it. I don't think it's fundamentally a problem.
Okay, great. So then maybe we can go ahead.
All right.
Thank you.
No worries. So in fact, what I'm talking about now is separation, and separation as far as transport primitives goes is harder than the transport itself. So just moving from A to B in a well of constant well frequency is relatively easy compared to separation. And the reason for that is that you can do this with constant trap frequency and you just get a coherent displacement, as we just talked about. When you do separation, you have to have trap frequencies change, and it will become clear why that is. And if the trap frequency is changing, other things can happen. For example, you can squeeze the motional state. And then the other problem is that if you have different masses, while you're doing these changes, because of the different inertia of the different masses, the ions react in different ways. So this separation is only easy to think about if you have certain symmetries, and that's the case I'll talk about here. If you have mixed species, these symmetries goes away and things become a lot more complicated. But again, I think it's just a matter of figuring out what to do it right and quickly. I can tell you something about the symmetric case, and this is what's shown here. You basically have to start maybe from a quadratic confining potential. So it's just a normal harmonic oscillator potential. And then you have to apply a strong fourth order. This is what this black thing would look like. That's the strong fourth order. And while you apply it, you can ramp the quadratic part down to 0. That's when you're in the black potential, and then actually flip the quadratic part around. So it has a spring constant that's smaller than 0. It's basically a repelling quadratic part. And together with the quartic, you get a double well potential. So that's essentially what's happening. And intuitively, you can already see this double well has to be on a scale where it counts for 2 ions that are trapped in this quadratic potential. Otherwise, you're not putting a plate between the 2 ions and separate them nicely. You're more or less putting something very blunt between them, and it's hard to separate them properly. This means that you would like to be very close to the ions to do these separations. And again, that's a motivation to make the traps as small as possible. You would like the electrodes to be near, so you can really make a double well on the scale or not too different from the scale of the distance of the ions in a harmonic potential. In any case, if you look at the theory situation here, for each of these pairs of Ks and K4s, which determine the external potential, we can solve the equilibrium condition. It's not solvable in a closed form easily, but you can do it and you can get the equilibrium distance. And then for this equilibrium distance, you can do the second order curvature matrix, and you can find the normal mode frequencies. This is all described in great detail in this reference here. I'll only discuss the salient features here. So once you do that, you can first of all talk about the normal modes. And basically here we start in a situation where the quadratic coefficient is larger than 0, so it's confining, and we have a constant quartic coefficient. So I can basically take the quadratic coefficient, go through 0, go to a negative, and what happens when I do that is the normal modes of the ions change from stretch mode and the center of mass mode. So those are more or less the modes in the quadratic potential. The quartic doesn't play a big role. Then you're entirely governed by the quartic when the quadratic coefficient is at 0. And you can see the mode frequencies move closer and closer together. And then finally, as the ions move apart in this double well situation, the normal mode frequencies are more or less the same. This just means the ions are so far apart now that their Coulomb interaction almost plays no role. And then the COM and the stretch mode have the same frequency. As far as separation goes, so this is just the equilibrium position in these wells as a function of this coefficient. This is more or less the separation in the quadratic potential, and it doesn't change a lot until the quadratic potential gets very weak. And then finally it starts to move. The separation goes up from this equilibrium separation to a much larger value. In this numerical example, it goes to 100 microns separation. So each of the ions moves 50 microns, one of them to the left and the other one to the right. The problem I already alluded to is that for such a separation, the trap frequency has to change because you start with the stretch mode and a center of mass mode that's very different in this more or less quadratic potential. And at the end of the day, when the ions are far apart, the Coulomb interaction is so small that the normal modes are essentially the same frequency. So no matter how you do it, you can maybe keep one of them constant if you're clever, but one of them has to move so they are the same while they are not the same in the same well, in this harmonic well. And so things become more complicated when you do this in a fast way. And so most separations that have been done in labs have been done in a more adiabatic situation where this happens rather slowly. I can talk about one experiment here that was the closest to where we would like to go so far. This was done with 2 beryllium ions. This is the surface trap we used. It's a gold metal on a quartz substrate. This distance here is about 40 microns, and we had 2 beryllium ions trapped, also about 40 microns. So this distance here out of the plane, away from these electrodes. We basically did the separation exactly as I described on the last view graph. We provided the strongest quartic potential that we could yield here by using all these electrodes to form a strong quartic. And then we had a smaller quadratic part, smaller in the sense that we apply smaller potentials to sculpt this quadratic part onto these electrodes. And we then inverted this quadratic potential. We just changed the sign of all these electrodes together. And when they go through 0, you're in an entirely quartic potential. I already said the ions were about 40 microns away from this center region here, out of the plane. So they are basically hovering over this chip. And here you can see the measured frequencies in the lab. Those are the dots, and these theoretical frequencies that follow very closely this example I just showed on the last view graph. So you start with the center of mass mode down here and the stretch mode up here, and then they approach each other. And once the ions start to separate, you have essentially the same frequencies for both of them. And that's also what we saw in the experiment. The deviations you can see here are probably due to stray fields. We are very close to a gold piece of metal here, and there's also dielectrics that can charge up. So we had stray fields, and that's one of the problems you have to practically solve to get better and better in these. The good news is we did this fairly slowly. The whole separation took about 500 microseconds. And at least in this adiabatic regime, we were able to keep the occupation of the harmonic oscillators relatively low. It wasn't quite as nice with the center of mass mode. You can see it goes from about 0.5 quanta or so up to 2.5 or 3 quanta, the stretch mode remained relatively cold. So it's not ideal, but you could imagine that if you do a separation like this and you had another ion to sympathetically cool, then you don't have to do a lot of rounds of cooling to go with your N bar from 2 or 1 back down to very close to 0 on the mode that you care about for the gate. And maybe for spectator modes, these numbers would already be okay. So this is by no means a perfect experiment, but it shows that in principle, the separation works like we model it, and we can now start and work on this. As I already mentioned, especially for a mixed species, this is really an active field of research, and there are not really great experiments at this point. But I think there are ways to do this, and I hope that these experiments will happen soon. So I guess we just had questions, so I'll just jump over this one, unless you have one or two that I can answer now.
No, there are none, so you can just go ahead. Thanks.
Okay, so I'll keep going. So to wrap up here as of the final maybe motivation, and to tell you that these ideas are not completely crazy, I want to jump over several things here that you will learn later in the classes, and just pretend that you know that I can do entangling gates between ions. Because what I would like to do is talk about an experiment that we have done about 2 years ago now. And the experiment implements a so-called gate teleportation. The idea here is that you have a resource, an entangled pair of ions, and you can split that resource between 2 remote places. So you basically take one ion and bring it close to this qubit here, and you take the other ion and you bring it close to this qubit. And then by doing the right set of gates onto these ions, you can implement a C0 gate between ion 1, which is the control, and ion 2, which is the target. And the amazing thing about this is that you can entangle, for example, these 2 ions, despite the fact they may have never met in their life. And of course, you have to pay a price for that. You need an entangled pair as a resource, and you also need classical communication between the places where this ion and this ion is located to make this happen. But it's still a very interesting primitive that could increase connectivity if you can apply it regularly in a big apparatus. And the way to think about it in this case would be that these entangled pairs can be a resource that you can produce all the time while you do the computation. So here entanglement is almost like the plug in the wall that you have to get current so you can run your laptop, for example. Now we are not using electrons that provide energy, we are using entanglement, and it provides a resource so we can entangle remote ions or other qubits, of course, if we can also do classical communication between these remote places. The way it works is the following. You first have to entangle this middle pair here. This situation is shown down here. You create an entangled state where either both spins are up. This is just one example of a Bell state, or both spins are down, and you cannot tell which one it is. But as soon as you look at one of the ions, the other one has to instantaneously also be in the same state. So this is what this Bell state says. 50-50 if you measure one of them, but as soon as you know one of them, you know what the other one is. This is this entangled Bell state that you have to prepare first. The other 2 ions can be in arbitrary states of their qubit levels. So A and B and C and D here. So the first step you do is you do a controlled NOT gate between one of these ions, which can now be separated in space. They just have to be close to B1 for M1 and B2 to M2. You do this controlled NOT gate. And what this controlled NOT gate basically does is it entangles this ion as well as these two. So now you have a tripartite entangled state. If you then measure the resource M1, you actually disentangle, because you're doing this measurement, this M1, but you leave B1 and M2 in an entangled state. And then you can also do, based on the outcome of this rotation here, a correction to M2. And that means that you are in a very particular entangled state. So if you measure spin up, you do something. If you measure spin down, you do nothing. And basically at this point, you have an entangled state between B1 and M2. And B2 is still not in the game yet, but that's going to change very quickly. You have this entangled state here. You do another C0 gate between M2 and B2. And essentially the same thing that happened before happens. You first get a tripartite entangled state between B2, M2, and B1. And then you measure M2 after also a single qubit rotation. And that takes M2 out of the game. Based on the outcome of the measurement, you do a final rotation here. This is where you need the classical communication. And here you do this final rotation, and the effect of all of that is that the final state of the magnesium ions is measured. You know it. You've done your classical communication based on that. And that leaves the beryllium ions in an entangled state that corresponds to a C0 operation with B1 as the control and B2 as the target. You can see that here, if B1 is in state spin up, the state of B2 has not changed, while if B1 was in state spin down, the state has actually changed. You can see D and C, these amplitudes have changed their meaning now. They are attached to spin up first for C and spin down, and vice versa for D. So that's a controlled NOT gate. This, you can read all the details about this in this paper, but now I would like to explain to you how this abstract idea actually looked in our concrete experiment. We were using a trap that had a lot of zones and also a junction, and we were loading the ions down here and then transported them up here to what we call our experiment zone. And here is a closer up of what it looked like in the experiment zone. We started with 4 ions, 2 beryllium and 2 magnesium in a single well. And the first step that we took is we have to create this resource, the entangled magnesium pair. So we did an entangling gate on the magnesium ions and put them into this entangled resource state. Then next, we were separating from the single well into a double well using that primitive that I was talking about last, but now with 2 ions in each of the wells. So you have to separate them in just the right way. So you end up with 2 ions in the left well and 2 ions in the right well. And your entangled resource is now split between 2 different locations. And you can start to do the rest of this. We had to do one more trick here. We only had laser beams in the center here because we use these free space beams and they're not easy to move around over all the trap. But in our architecture, rather than moving the laser beams, we can move the ions so they come back into the laser beams. So that's what we did here. We first took the left pair and shuttled it to the center. And now we can interact with the same laser beams. We can do this C0 operation and then measure the magnesium ion. So that's what's happening here. In the next step, we change the conformation again. We are done with this part here now, and we want to work on the other 2 ions. So we move them into the laser interaction zone. And the first thing we did is we did the corrective rotation on the second magnesium ion based on the outcome of the first magnesium ion measurement. Then we got ready to do the next C0 and did the next C0. Again, we are measuring the magnesium at this point here. And then finally shuttle the beryllium-1 ion into the interaction zone again to do the final rotation for doing the correction based on this measurement here. And so after all this is done, we have basically done a C0 gate, but of course that's only what we ideally think we've done. So what we did after this is, when we are done here, we first also measure the beryllium ion, and then we shuttle the crystal a final time and measure the other beryllium ion. And we've repeated this experiment for a lot of different input states of the two beryllium ions, so we could do so-called process tomography. And this is what we saw. The ideal C0 in a representation where you have Pauli operations here. So these are just different ways you can rotate your two qubits, and you can look at the process matrix in this basis. This is what the ideal C0 would look like. And this is what we saw in the experiment. So you have to really look very precisely to see differences here, because the errors, they are substantial actually, but they're spread out over all these matrix elements. So to help you a little bit, these are the differences. And you can see these differences are non-zero. They just seem small compared to these larger elements in this process matrix. And so basically the gates to entangle the magnesium ions, this one had a fidelity of 0.96. And then each of the mixed species gates, two of them that we had to use for the teleportation part, had a fidelity of about 0.97. But these things all compound very quickly. So looking at this process here and doing estimation of the fidelity using certain mathematical techniques that I'm not going to go into the detail, we were able to estimate a process fidelity in a 95% confidence interval of about between 0.84 and 0.87. So the moral of the story is we can do single or we can do entangling gates between two ions at fairly high fidelity. Those are not the record fidelities. Actually, there are experiments that can do 0.99 something. It's fairly high, but as soon as we do more than one of them, the errors quickly compound. And so if you do a primitive like gate teleportation, for example, you go down to a fidelity on the order of 85% or so. So we have to still do a lot of work, but in principle, this idea of the CCD, quantum CCD approach with trapped ions seems to be working. And so we are very hopeful that we can continue to improve all these processes. And I think that is the end of my presentation. I can take a final round of questions if there are any.
Okay, so there's at least one question. So let me first read it out to you.
Can you maybe move closer to the microphone?
Can you hear me?
Now it's much better. Thank you.
Okay. So the question is, do you know of ongoing efforts to exchange quantum information between ions in different traps by enhancing their Coulomb interaction using an electrically conducting antenna or wire?
Yes, I do know about such efforts. I'm not sure whether they are currently ongoing, but in Hartmut Hefner's group at the University of Berkeley, exactly this kind of experiment was pursued for at least 5 years or so. And the last I heard is that it's still very hard. The problem is that the wire that connects these two ions has to be completely disconnected from everything else. And so basically you have a floating piece of metal. And oftentimes if you have a floating piece of metal in an experiment, it can charge up very quickly and change the potential that the ion sees. And so that was the main problem. The other technical difficulty is that this wire has to have a very low capacitance, because if the capacitance is high, you're basically diverting the quantum information onto a lot of other charges, electrons in the wire, and all of them have a chance to decohere. It gets very hard to transport the quantum information, and the process also gets slower and slower the more capacitance you have. This is a very hand-waving explanation, and there are several papers that explain all of this in more detail. So the answer is, it has been attempted. I don't think it has been successful at this point in time. So it's a tough problem for technical reasons mostly. In principle, it could work.
Okay, next question. What is the minimum temperature required for your ion to implement entanglement?
Oh, so that depends on the quality of entanglement. If you just want to be barely entangled, which means your Bell state fidelity has to be larger than, say, 0.5, so that's the limit, you don't have to be very cold. But to be useful for scaled up quantum information processing, I think fidelities have to be 99.9 or even larger, so maybe 4 nines. And so far, to reach fidelities for like 3 nines, you have to be very careful about ground state cooling. I would say for spectator modes, you want to be at an occupation of below 10%, 0.1. And for the mode you're doing the gate at, you want to be even lower. And this is despite the fact we are using first order insensitive gates like the Momo-Sorensen gate and geometric phase gates. So even in that scenario, you have to worry about the temperature, and you also have to worry about the anomalous heating. So even if you cool to a fantastic N bar, the fact that your ion is heated by the noise fields in its environment can spoil these gates, and you have to take a close look at those rates as well to get the highest fidelities. So for useful computation, you still want to be very close to the ground state.
I think this one is, next one is in similar lines. So how do you ensure that entanglement is preserved during transport or separation?
That's a very good question, and I kind of swept that under the rug. The way we ensure that transport and separation don't affect the internal state of the qubits is that we want to completely have these states separable. So what that means is the motional state of any of the ions and their internal state, their qubit states, cannot be entangled at the end of the gate. Your gate has to be clean enough that no residual entanglement remains. Once that is true, you can act on the motional state, and since it's separate from the internal states, as long as you're not doing anything that is particular to the qubit states. So if you're just grabbing onto the charge by changing the external potential, you don't have a problem. Of course, when you want to do the next gate, you have to use the motion, and you have to make sure that it's in a clean state. So you have to cool the motion, at least of the mode that you do the operation on, very nicely. And at that point, you still have a separate state between motion and the internal states, but that separate state on the mode that you're doing the gate is a clean, nearly pure quantum state again, and you can use it for the next gate. After that gate, you better be separable again, otherwise your transport will be detrimental to the qubit information. So that's the basic idea. Make it separable while you do transport, and only entangle the motion with the internal states while you're doing operations, multi-qubit operations.
Okay, so there's another one. So is the measure you use for entanglement for the multi-particles a witness or a measure? So what kind of thing we use? Is it a
it is a what?
Witness or a measure?
I'm not sure how to answer that question.
So let me ask. So would you, Saikat, would you like to pose the question yourself?
Yeah, I was basically asking whether this is an entanglement witness or this is actually a measure of it, because beyond bipartite.
Oh, I got it now. Okay, I understand now. So are you talking about the teleportation experiment?
Yeah. Mm-hmm.
Okay, so in this case, it's more than a witness. We really look at the process. We put all, we call it informationally complete number of input states, so many different input states, run it through the gate teleportation, and then do a state tomography on each of the output states. In this way, we can characterize the whole process as a process matrix, and we can characterize the operation fidelity, so the process fidelity. And that is more than a witness. Basically, a witness just tells you whether you're entangled or you're not entangled. If I have the process fidelity, I can say I use an unentangled state as input, I run it through this process, and I get a certain fidelity, which is governed by this whole process matrix that we've completely determined. So I can basically, for any input state, predict what the fidelity of the output state will be. And in particular, if the input state was an unentangled state and the output state is a Bell state, I can tell you what the fidelity is. And that's more than just a witness, because the witness would just tell you whether you're entangled or not. It's like a border patrol that tells you, am I an unentangled country or an entangled country? And we can do a little more than that.
Okay, thank you.
Okay, so there's one more question which is relates to the chip picture that you showed on your last slide. Mm-hmm. And the question is it made of silicon or is it made the way RF antennas are made, like PCBs?
So this chip, I should maybe have mentioned that the white material that forms the substrate is aluminum oxide, alumina, and the electrodes are gold. So aluminum oxide or alumina is indeed a nice material to also do microwaves. In our case, we are using it because we run fairly high RF voltages to confine the ions. This is one RF electrode. There's actually another one below this electrode here. This is a 3D trap structure, in fact. And this RF, since it's at very high voltage, you don't want losses in the chip, because then the RF would not only trap the ions, it would also heat up this whole chip. And high temperature leads to higher anomalous heating, and it can also destroy the chip. That's why we are using high quality materials with low losses at RF. And alumina is also very nice for microwaves. So if you want to run some microwaves on this trap, this one doesn't have any microwave electrodes, but in a future version, we would probably have microwave electrodes on it. You can definitely use alumina, which we used here.
Okay.
For silicon, actually, since that question was asked, you can use silicon at low temperatures if it's highly pure silicon, and it also has very good features. At room temperature, you can either, for example, put boron into the silicon. So you basically put boron in as conductors, and it can be relatively low loss, or you have to use very high quality silicon. But at room temperature, it's not so easy. When it's cold enough, the silicon, it's also a good RF material or microwave material.
Okay.
All right.
So I don't see any other questions. So I think we should conclude, and thank you for your very nice set of lectures. And I think we can applaud if that would be great. Yeah.
Thank you for inviting me, and I hope that there is some benefit from this. At a minimum, maybe you can look at the literature that I was talking about, and maybe a lot of things that weren't so clear when I was talking about them will become more clear.
Yes, I think that will be very helpful. Anyway, you have made all your slides available to us, so we'll put them on the website as well.
Yeah. In fact, I will update the slides because I went through them yesterday and found a few more typos and things like that. Yes. I will update the slides once more, and that will be the final version. This should happen in the next hour or so.
Okay, that's great. Thank you very much, Professor Leibfried, once again, and thank you everyone else for joining in. So
you're very welcome. And I wish you great success with your school.
Thank you. Thank you. Yes. Okay, good night, everyone, and we'll meet tomorrow again in the
All right.
afternoon.
Yeah, good night. Good night.
Good night.
Good night.
Good night.